Hey guys, welcome to this video where we will be exploring the Hall effect. And to me, this is one of my favorite, this super cool effect that was discovered by Edwin Hall in 1879. And still to this day, we use so many different kinds of Hall sensors, is what we call them now, to do a variety of different things. And it's one of the best and most interesting applications, obviously besides the motor and the generator, of magnetic fields in use. So let's jump into it. So we've seen the effects of a magnetic field on free moving charges and currents, and now we're going to see that the magnetic field also affects charges that are moving in a conductor. So the Hall effect is basically where we take a metal plate, sometimes called the Hall element, and we attach a potential difference across these ends of the plate. Doing this will yield a current running through. Now we have to keep a track of thinking of this as conventional current, and that's the way I'm going to talk about it first. Now, in terms of conventional current, we would have the current flow from left to right in the bar as I have it drawn over here. Now, what the Hall effect is really showing is that when I bring a magnetic field to this piece of metal, this plate, let's say I have it pointing out of the screen. So in other words, I have some magnetic source behind this bar, seen here in the side view, and it's pointing this magnetic field out of the screen or through the metal bar. So if we take a look using the right-hand rule, we can see that if the magnetic field lines are pointing out of the page, and I'm using conventional current here, so I have a positive charge carrier moving to the right, and that shows that the magnetic force is pointing down. So it's going to push these positive charge carriers towards the bottom of this plate, and thereby leaving the negative charge carriers, or more negative region, at the top of the plate. Now hopefully it's pretty clear that if I attached a voltmeter across these ends of the plate, I would see pretty clearly that I have a potential difference that's been established in the presence of a magnet. Now, of course, there's not direct contact of the magnet with the bar, but in its presence, we have seen some sort of deflection. Now, this potential difference across that was established in the presence of the magnet is known as the Hall EMF, or the Hall voltage. And it's this voltage that was discovered by Edwin Hall, and he was an American physicist. In the late 1870s is when he discovered this, and that's named after him. So basically what this allows us to do is say that in the presence of some sort of a magnetic field, I will establish this little micro voltage across the bar, and this will indicate to me that there's a magnetic field present. So a lot of magnetic field sensors will use this Hall effect, because in the presence of a magnetic field, it will establish that voltage, which is not there when there's no magnetic field. So one way we can think of this measurement is that in the presence of a magnetic field, we would detect a microvolt per unit of magnetic field strength. So an example would be a microvolt per Gauss. And that would be sort of a unit that we could use to describe how much voltage there is per unit of magnetic field. Now, to me, one of the coolest things about the Hall effect is that it was actually used to determine whether positive or negative charge carriers were actually carrying the current through the wire. Now, it showed very fundamentally that in metals, a lot of the time it's negative charges that carry the current, whereas in some semiconductors it's shown that positive charge carriers can actually carry the current. So that's a pretty neat idea, and you can think about this if you look at actual current, so the movement of electrons, versus conventional current. Alright, so in this image that you see here, I am showing two Hall elements, or two Hall bars, if you will. But what I'm not showing is that each one is connected to a potential difference in the same orientation. So in other words, there's a wire attached here on this end and this end to a power supply, and the same thing occurs over on this end. Now we have to keep in mind that because I'm showing that conventional current is pointing in the same direction in both cases, that means that this end is connected in both cases to the positive terminal, and this end in both cases is connected to the negative terminal. Now the voltmeter that you see connected here in both cases is what I'm going to use to show the Hall EMF. And remember, that arises when I have a magnetic field that's nearby a current carrying Hall element. Okay, so let's start with this first example up here. Now this is where I'm going to have a positive charge carrier, and the positive charge carrier we know is being pushed to the right. This is the one that we already used before. Now keep in mind that we also had our magnetic field oriented out of the page, and so if I have the magnetic field out of the page and the charge carrier pointing to the right, I'll have the magnetic force pointing down, which we see the result of in this image. So there's all the positive charge carriers have been pushed down here, leaving this end to be more negative. Now in this example down here, we still have a conventional current in this direction. In other words, we're still having this end over here being attached to the positive terminal of the battery. But if this were appearing to be conventional current, but actually had electrons flowing, if I add a negative charge carrier, which we know based on the setup that we have right now, it would be moving to the left because it's attracted to the positive terminal of the battery, if you will. So I take my left hand, I still have the magnetic field pointing out of the page, and I have my electron moving to the left, and my thumb still points down. So you see down here, that is the result. All these little negative charge carriers have been pushed down here to the bottom, leaving this top region more positive. So how the heck will I use this now to tell me what actual charge carriers are moving through the current? Well, remember, I set it up in both cases exactly the same. So I have the battery facing exactly the same way in both cases. Now, when I look at the Hall EMF, what would be measured here on this voltmeter, I would see that I have a negative EMF in this case, let's say. But for the exact same setup, if it were negative charge carriers, I would see a flip or a positive EMF, Hall EMF, that results. So what we find is that the direction of the field and the current are known, then the sign of the charge carriers can be determined by the Hall effect, which is pretty neat. So in metals, we see this actually be the case, right? We have our battery set up with the positive terminal over here and the negative terminal over here, but we still have a Hall EMF that results from this kind of orientation of the signs, which indicates negative charge carriers. Now in some semiconductors, like we mentioned before, we will see positive charge carriers. It would look something more like this. Now, what was discovered in the early 1980s was that the Hall effect is also actually quantized. So it's showing quantum behavior in an object that from a distance or from a macroscopic perspective is just sitting there, right? Or just has conventional current running through it. But within it, we actually see that there is quantum behavior. That's very similar to what we talked about when we were discussing how charge is measured, and that charge is quantized. In other words, it can only come in discrete units or increase or decrease in discrete units. For me, one of the coolest applications of a Hall sensor is a wheel speed sensor in a car that basically measures how many rotations per minute the wheels are making. Now, the rotating shaft of the wheels, we often will have a trigger wheel attached to that, and it's basically this mechanism that looks something like this, and it has these, what I'll call, for lack of a better term, these little spokes along the sides of the wheel. Now the Hall sensor is over here on this side, and there's a very small gap between those spokes of the trigger wheel and the actual sensor. there's also a permanent magnet. Now, every time the wheel turns and the gap difference is detected by the sensor, we will see that there will be a different voltage measurement or a Hall EMF measured across the Hall sensor. So if we were thinking of a graph of the voltage versus time, we would see these high values, low values, then high values and low values of this voltage, of this EMF. And that over a period of time, within a minute, we could use that to calculate the number of rotations that has occurred in that minute. Now this is a square wave, and that's very easy to convert into the number of rotations per minute. So that's just one of the really cool Hall effect uses. So hopefully you found that kind of interesting, and we will come back and actually discuss the Hall effect again in a little bit more detail when we have concluded a little bit more of this magnetic course.